All right, good afternoon, everyone. Let's see, the projector is not working. There we go. Okay. So today is a pretty important day. We're going to first review some of the probability material that we're going to be using quite a bit from now on. And then we're going to start to talk about one of the most important results or viewpoints that we're going to use all semester, which is the bias variance trade-off. So just to sort of recap where we are, in the last lecture, we were looking specifically at the case of degree D polynomial regression. And what we saw is that if we choose the polynomial order D too small, that causes underfitting. The model is too simplistic. It can't really follow the trend in the underlying data. On the other hand, if we choose D too large, it causes overfitting. What happens is the model starts to fit the noise in the training data, and we expect to have different noise in the test data. And so basically, it's a bad thing that it's fitting a quantity that we won't have in the test data. And what we saw is that a solution to this is we can optimize D by minimizing the sample mean squared error on the test data through cross-validation. We talked about several different cross-validation procedures. One was simply splitting into training test. Another was k-fold cross-validation. Yet another one was k-fold cross-validation with the one standard error rule, so in increasing complexity. So what I want to emphasize now is that that's just like a special case of what you see in general in machine learning. In general, what you see is that models that are too simple cause underfitting. So it's not just about polynomials, it's about any kind of machine learning model. Models that are too complex cause overfitting. And there's different ways you can adjust that complexity. You might be using something like sample MSE, you might be using some other metric. But the point is, depending on what kind of task you're working on, regression, classification, or so on, you're going to have a different metric. But as long as you look at some sort of test-based metric using cross-validation, you can tune that complexity. So we'll be doing this all semester long. Now, coming back to the special case of regression, where we're looking at mean squared error, what we're going to focus on now is replacing this sample mean squared error with a new quantity, which is the statistical mean squared error. So in order to define that, we're going to start by talking about random variables and so on. And what we're going to see, hopefully by the end of the lecture today, is that we can derive an expression for this statistical MSE that decouples into three very intuitive terms: bias, variance, and irreducible error. This irreducible error is something we can't do anything about, so you just sort of forget about it. It's there, but we can't really minimize it. But the bias and variance, what we'll see is that as we change the model complexity, we're trading off one for the other. So when we have a really simple model, we're going to have high bias, low variance. As model complexity goes up, we're going to see the bias goes down, the variance goes up. In the end of the day, both of them are important because both of them contribute to mean squared error. So you have to get the right trade-off, the right balance between them. So that's what we're going to see at the end of all this. So that's just sort of a quick introduction, but now let's get into it for random variables. So this is the first time we're talking about random variables in this course, so I'm assuming you guys have seen these before in some prerequisite course. However, might have been some years ago. It might not be fresh in your mind. So I just wanted to spend a little bit of time establishing some notation and bringing back some of those traumatic memories from your probability class. So, so first of all, why do we even care about randomness? So it's a really useful concept when we deal with uncertainty, when we design engineering systems, and we don't really know what's going to happen. So it's just a way that we can tractably construct a world of possibilities and navigate that world. So that's essentially why we care about randomness and probability and stuff. So now let's talk about random variables. What are they? So a random variable is really different than your typical algebraic variable. It's a totally different beast. And so one analogy that I like to give is a bag of marbles. So imagine that I have this big bag of marbles. Every marble has a number on it. So what I can do, I can take this bag and I can draw numbers out one by one. Every time I draw a number out, a marble out, it has a potentially different number on it. So now I might have a bag where all the marbles I draw from it are either zeros or ones. That would be essentially like one type of random variable. So the random variable is like this bag. So I could have a binary random variable, so every time I draw what we call the realization from it, it's either a 0 or a 1, never anything else. Now that's maybe not it. You might have a particular bag of marbles where 2/3 of the marbles are zeros, 1/3 of the marbles are ones, and there's no other kinds of marbles. So for that kind of bag, that would have a certain probability of drawing the 0, a certain probability of drawing the 1. That's again an example of a particular kind of random variable. Now, you might have a different bag of marbles where every time you draw a marble, it has a real number, right? So that's quite a different bag of marbles than the binary one. But again, like the property, the random variable is the entire bag. It's that whole world of possibilities. And more than that, it's like, it's a particular, it's a particular world where maybe the zeros come out twice as often as the ones. Okay, so hopefully that analogy is helpful. When you think about random variables, it's more than just an algebraic deterministic variable. It's like this whole bag of marbles. Okay, any questions on that? Okay, so when we talk about random variables, we generally have to talk about them in two specific cases because some of the math varies. They're either going to be discrete or continuous. So a discrete random variable is a random variable that takes on values from a countable set. So for example, we talked about binary 0 or 1. It could be 0, 1, 2, 3, 4, or it could be all the integers from -infinity to infinity. Those are all countable. When we talk about continuous random variables, these are cases where you have the random variable taking on an uncountable number of possibilities. So when you look at real numbers, it's a different level of infinity than a countable infinity. It's really like you can't even enumerate them in a list anymore. Even if you look at real numbers between 0 and 1, there's no way you can put those in a list. It's a bigger kind of infinity. It's the uncountable infinity. So this sort of at a high level, this is how we break things up when we start writing things down mathematically, because the math is a little bit different for discrete versus continuous. Okay, so in this discrete case, it's a little bit simpler. We're going to use these superscripts here, like 1 through k, to denote the possibilities that this random variable can take on. So in this case, it has capital K possibilities. So perhaps it could be like 1, 2, 3, 4, 5, 6, 7, all the way up to k. And of course, k is going to be generic here. And so in addition to saying what are the possibilities the random variable takes on, we also have to say how often do those occur. And to describe how often they occur, we can have a vector of scalar probabilities. So this first element in the vector is the probability that you draw A1. The second element here is a probability that you draw A2, and so on. The last one is a probability you draw AK. Okay, so that's sort of all there is for these discrete random variables. If you know the possibilities and how often they occur, you know everything about this random variable, this discrete random variable. There are some rules about how these probabilities can be constructed. So first of all, as probabilities, they can never be negative. They can never exceed 1. And when you sum them all up, they have to add to 1. So those are the rules on the elements of this vector. And this vector, here I'm writing it with a bold P to denote it's a vector, that has a special name of the probability mass function. So with a discrete random variable, again, you have these k different possibilities, and then you have a vector, the PMF, that tells you how often they occur, and that's it. Okay. Any questions on this discrete case? Okay. Now, when we move on to continuous random variables, it's a little bit more complicated because, again, the main thing that changes is now, instead of just having a list of numbers, we have a continuum, uncountably infinite set. So one way to think about it is through this cumulative distribution function, or CDF. In some ways, that's the easiest one to state. So this, and by the way, just for these slides, I'm always using capital letters for random variables and small letters for discrete, for deterministic ones. Like these are deterministic, these are small, but this A is random, so it's big. I'm only doing this for a few slides, and this is consistent with what you see in probability books. But when we move back to machine learning, we're going to use the same variable, like boldface, little x is vector, boldface, big X is matrix, and so on. So this is just for a few slides. I'm doing it the traditional probability way. Okay, so here when we say what is the CDF of the random variable A evaluated at the fixed value little a, this is just the probability that that random variable is less than or equal to that value little a. So that's what how the CDF is defined. And now, we're not going to use the CDF much in this class, just once in a while. What we'll use more often is the PDF. The PDF, if you want to state it officially, it's the derivative of the CDF with respect to that argument. It's maybe not all that intuitive, but that's how it's defined. And you can understand it a little bit from this integral here. So if you're saying, what is the probability that the random variable A, capital A, is less than or equal to this little a, then you construct an integral where the upper limit is that little a, and now you plug in this PDF, and now you have to use a different dummy variable than that. This is just anything you want to call it as long as it's not a. Okay, so, and then from this definition and the fundamental rule of calculus, you can see that you get this. Similar to our probability mass function, our PDF needs to be non-negative, and it needs to sum to 1, although now instead of a sum, we're kind of replacing that sum with this big integral. Unlike the PMF, unlike that, it's not upper bounded at 1. This PDF can get arbitrarily high. So that's a little bit different. So there's a lot of information on this slide, and I don't expect you to have this all in your brain right now. So I did write a 7-page document that's sort of textbook style that just goes through this stuff as well as the stuff on the next couple slides that you can read. That's a lot, it's a lot less dense than this. It's just prose. And if you want to review this, you can go back to your probability book from whatever class you took, or if you've sold that or whatever, lost it, you can read this, which is just kind of a slower explanation of all this and so on. Hopefully it's useful to you. Okay, so that's just starting out with the definitions. Any questions? Okay. Moving on to expectation. So we're not really going to do a whole lot with probability in this course. We're going to focus on expectation, which is one particular little thing we can do with random variables. And first, what is it? It is the statistical mean of a random variable. So the first thing I want to do is I want to contrast that with the sample mean. The sample mean is something we saw back in Unit 1. So if I give you a list of numbers like 1, 2, 3, you can easily take a sample mean, right? You just sum up the numbers and you divide by, in this case, 3. If I give you a list of numbers, can you take the statistical mean? No, because we haven't said anything about what is the probability model that we're giving to these quantities. So to take the statistical mean, it has to be a random variable. There has to be a random variable somewhere in there. That random variable has to have either a PMF or a PDF. That's the difference. Sample mean is just like a simple deterministic little function. You can apply it to deterministic variables. You can apply it to random variables. Whereas statistical mean, you can only apply to random variables. Okay, so this is of a random variable. Okay, so what is this thing? What is the statistical mean? How is it defined? So if we have a discrete random variable, we can define it this way. We sum over our capital K possibilities. And this is actually, what I'm showing you here is the statistical mean of a function of the random variable. For example, maybe it's the squaring function, a squared, or maybe it's the log, or maybe it's the trivial function that does nothing. In any case, what you do is you apply the function to that possibility, like that, and then you multiply this times the probability that that particular possibility occurs for this random variable. So that's the kth element. Oh, actually, I need to swap these. I wrote it A, comma, K. And so that's just the kth element of that PDF. Okay, so this is how expectation is defined. And if you ever are curious about some property, does it hold or not for expectation, just come back to these definitions. Most properties can be verified from the definition in like 1 or 2 lines. It's usually pretty easy. If you forget, like, oh, I didn't memorize that, just come back to the definition and then just prove it. It's usually very easy. And you'll get some chances on the homework. Okay, so this is a discrete random variable. What if it's continuous? Now we're going to have an integral over the entire real line. And we're going to have, again, f of some dummy random variable. We'll call it a. And then we're going to have the PDF, PA of little a, and then DA. Okay, so you can, again, imagine f being any scalar function. Like if you want f to be the squaring function, you're looking at what's the expected value of a squared. Then it says you just square this. All of this remains the same. Or you square this part. This is untouched. Okay, so that's expectation. That's the definitions. Often in our class, we'll actually deal with vectors of random variables. It's just like a vector that has a collection of these scalar random variables. We'll talk more about those in a moment, but it's not really any different than this. Are there questions on these definitions? How many people find this comfortable versus how many people just sort of don't remember too much about this? Okay, it's okay if you don't. All right. Okay, so we won't work too much with these raw definitions. We will focus on 2 key properties that we will use over and over and over. So if you can master these properties, that is 99% of what you need to do. These are properties of expectation. So we're going to now imagine that we have 2 different functions, f and g, playing the role of this here. And let's say that we have 2 different random variables, capital A and capital B. So the first thing is, what happens when we do the expectation? Oh, and by the way, these little c and d, these are just deterministic scalars, like, you know, some number, they're non-random. So the only randomness here is in this random variable here. So if you look at what is the expectation of this, to figure out what this is, imagine you take this whole thing and plug it into here, which basically replaces that part. And now you can kind of see, because integration is linear, when you stick this inside the integral, you're going to get a first term, which is going to be c times this, right? But because that integral goes to 1, because we said that the density integrates to 1, you will just get, for that first term, c at the end of the day. Now, you also have this other term by linearity of that integral. And so you will have GFA inside here. But as you know, you can pull the d out to the front. And then you just have the FA that remains, which is this. So you get d times the expected value of f of a. Okay, so that's the first rule. That's the linearity rule. And so we'll see this a lot. So whenever you see some scaling and adding of random variables inside an expectation, just know you can break the expectation up. You can pull all the scaling constants outside, but the random variables have to stay inside. You have to dig a little harder to see if those can be simplified based on some property of the function and the random variable. Okay, so any questions on the linearity property? Is that making sense? Okay. The second property is when you have inside this expectation a product of two different things that involve two different random variables. So in general, you can't really do anything with this. You're stuck. But there's a special case where if those random variables are what we call statistically independent, then you can break up that expectation into a product of two expectations. Expectation of the first, FA, times expectation of the second, GB. Okay, so this you can do only if they're independent. Otherwise, you are stuck here. What does it mean for two random variables to be independent? So if you have two random variables, you can define a joint PDF, very similar to the scalar PDF we saw before, but now there's two random variables and two arguments. And when they're independent, that joint PDF factors into product of those individual PDFs. And if you use that inside this definition here, you can easily prove this for yourself. Okay, so those are the two properties that we're going to use a lot, linearity and independence of expectation. We'll use those over and over again. There's a bunch of practice problems on the next homework where you can practice this stuff. All right, any questions on these two key properties? Okay. So, not surprisingly, after we're done talking about expectation, the next thing we talk about is variance. So variance is defined very similar to how we define sample variance from the sample mean. You can define the statistical variance from the statistical mean. It's just that the averages are now expectations. So we have the expectation of the difference between, A minus its mean, quantity squared, and now we average that. So this is how we can define the variance. And similar to how when we define the sample variance and we went on to show an alternate form of it, we can do the same thing here, and we get expected value of A squared minus the mean squared. Okay, so again, the main difference between sample mean and statistical mean, sample mean involves a summation and a normalizing thing, whereas statistical mean uses the expectation. So if this was sample mean, then this would be that 1 over n sum over n, 1 over n sum over n, and so on, but now it's expectation, expectation. Okay, to use the expectation, you have to have random variables. To use a sample mean, you don't need random variables. You can do it with or without random variables. All right, so that is expectation. Is everybody good with that? Okay. Conditional expectation now is the next important concept. So this is where things start to get a little trickier. So the conditional expectation is the expectation, in this case, of a function f of random variable a. And here's the key idea. Given that some other random variable, which we'll call b, takes on some specific value little b. Okay, so maybe one example is a could be whether it's raining or not in Columbus, Ohio. B could be the month. So clearly these two things are related. You know, if I told you that the month is summer and I ask you, what is the probability that it's raining? You might say, 10%. Now, if I told you that it's January, what's the probability that it's raining? Much higher, right? So there's this interaction between the random variables, and here the mean of this, we're saying, is going to be influenced by the value that this other random variable is taking on. So for us in machine learning, this is super important because we have features and targets. We're asking questions like, what is the value of the target given that the feature takes on this value? That's exactly how we're going to use this, or one way we'll use it. Okay, so how is this defined? It's defined very much like the original expectation. All we have to do is change the probability function. So here's the integral that we had before. Here's the f of a that we had before. The only difference now is instead of our typical PDF, now we're going to have, we call the conditional PDF, PDF of a given b, and this is going to be evaluated at, first of all, there's this dummy variable of integration that's going from minus infinity to infinity. We'll call that little a. But second of all, here's the value b that we're saying that the random variable b takes on. Okay, so this is the definition of the conditional mean, and all we did is we swapped the PDF with this conditional PDF here. Okay, so questions on this guy? Again, I realize I'm going through information pretty quickly here. I'm covering a lot of ground, but you can see all this on your own time, explained hopefully clearly in this 7-page document. Okay, so this is, I think, the easiest way to start with conditional probability. So or conditional expectation, the value of this, you can see, will clearly depend on the value of little b. Yeah, so if I plug in for little b is July, you get one probability or one expectation. If I plug in January, you get another one. But sometimes what we see is this is left out. So it's like you'll just see this. Okay, so essentially the easiest way to understand that is just replace that little b with a random variable. So in other words, in this expression, instead of this little b taking on this value, just replace it with a capital B, and that is the definition of this. Okay, so what that means is, whereas this is dependent on this deterministic little b, now this is actually random because I'm plugging in for that little b a whole random variable, and now this thing is random. That is a random variable. This is, as a random variable, you can look at its mean, its expectation, its variance, whatever. Whereas this is deterministic. it doesn't really make much sense to look at its mean or variance because it's just a fixed deterministic number. So this is not. Okay, so that's this thing. And let's talk about 3 useful properties that we'll see. So if you have some functions, random variable a and g of b, inside this conditional expectation, what you can do is, for the purpose of this expectation, you can treat this random variable as if it was deterministic. So wherever you see a inside here, pretend for a moment that it's deterministic. So if this is deterministic, we know from the linearity property, we can just pull it out of the expectation. So that is how you can deal with this. So this becomes f of a times that other thing, expectation of g of b given a, or conditioned on a. So this is the main idea. When you see this, I'll say treat expectation as if a was deterministic. Now, it is not deterministic. It is definitely a random variable, but just for the purposes of this expectation, you can pretend that it is. All right, second, if a and b are independent, this one is kind of intuitive. If you see something like expectation of f of a given b, essentially it's sort of like saying, what is the average value of f of a given the value of this other random variable? Well, okay, if these random variables are independent of each other, this b tells you nothing about a, and it doesn't matter if you condition on it. So essentially, when they're independent, you can just drop that conditioning altogether and just write expected value of f of a without any conditioning. Okay, so that's, again, only if they're independent. In general, you can do that. And the third useful property that we'll sometimes see is this nested expectation. So like, let's say you start with this conditional expectation. Remember that this is a function of this random variable b. So this is itself random. So I could take one more expectation, this outer one, and that outer one essentially says, let's average over all the possibilities of b. Well, it turns out when you do that, you get back to expected value of fa. So this is known as the law of total expectation. It's just a nice simplification that you can apply with nested expectations. And sometimes it actually helps you derive something. You just do one expectation at a time, telescope out, and tackle a complicated problem that way. So again, all of this is explained in a more leisurely, at a more leisurely pace in this document. Okay, so I think this, yes, this sets us up for what we need from probability for our machine learning. So obviously there's tons of other concepts in probability, but the good news is we don't really have to worry about them. This is enough for us. Mainly just expectation, a little bit of variance, conditioning. That's it. Okay. Before we move on, are there any questions? Yes.
So is the expectation of f of a given big B, is that like, so that changes, and it's like you're picking, with your month and rain example, it's like you're picking a random month and seeing what the expectation is?
Yeah, it's saying, okay, I know the expectation depends on the month, and now I'm holding that month random, so this whole thing becomes random. Basically, yeah.
Can you clarify what you mean when you say deterministic?
So deterministic means non-random. So either you have random variables, or the things that are not random variables are just deterministic. Okay, good questions. Any other questions? Okay, so yeah, hopefully we can now start applying these concepts, making them a lot more intuitive and understandable if they're not intuitive to you already. And so what we're going to do is we're going to establish a statistical model, which is how we're applying all these random concepts to machine learning, and then we'll analyze that model. So the statistical model in Spirit is very much like how we set up our demo for this unit, if you remember that polynomial demo. So first we're going to assume that we have some true model that is the form target equals some function of the feature vector x plus a noise. Now, in the demo, the noise was Gaussian. Turns out now we don't actually need to even say what the distribution on the noise is. All we need to know, or all we need to fix, is that the noise is zero mean, and then it has some finite variance, which we will call sigma squared. This model holds for training and test quantities. So this is how you could think that the true data is actually generated. So there are some features x. There's some true model. In the case of the demo, is a third order polynomial with particular coefficients. And then there's a random noise added to it, and that's how you get the target. So these may be training features, training noise, training targets. They could be test features, test noise, test targets. We're assuming that the test and training all come from the same model. They're consistent in that way. Okay, so that's sort of the setup. Now, what are we talking? What are we considering random and not? So, as I mentioned, this noise epsilon, that is random, with mean 0 and variance sigma squared as above. We will also think about the feature vector x also as random. This is useful because it's sort of like saying, when I apply this thing in the real world, that I don't really know what that test vector is going to be. I really want to know what might happen on average or what might happen for specific cases, but it's important to think about it as random. Now, the feature vector x sort of makes sense to think of that as statistically independent from the noise. The noise is just sort of generated on its own independently of how the features are generated. So that will greatly simplify our lives, and it's true, I'd say, in most situations, or most definitions of noise are independent of other stuff. And we'll also have to make just a few more assumptions to clarify and simplify. So all of our test feature vectors, they're all random, and they're all independent of each other. All our test noises are random and independent, and they're independent of those training features, training noises, and also the test features and test noise. These are all random things. They're all independent of each other, mutually independent. So when we see them together inside expectations, that's nice because we can split them apart. Okay, so that's the true model. Now, there's a separate model that usually, in practice, does not agree with the truth, and that is our prediction model. So because it's different, notice we put a hat on this f. So like this might be a third degree polynomial. This might be quadratic polynomial. Or it might be logarithmic. It could be anything. Another difference is that this one depends on some parameters beta that we have to learn. And those parameters are designed from the training data. So, we'll assume that there's some training process. You take in the data, you put it through this black box, out come the parameters beta hat. Well, because the training data, those x and y's were random, so are these parameters. So we're going to think about these parameters as, or the parameter vector beta as a random vector, a vector of random variables. But because of the independence between training and test, we can say that the beta hat vector, which is based on training quantities, is going to be independent of the test quantities x and epsilon. So those are mutually independent. Okay, so that's basically our model. Simple as that. Prediction, truth, a lot of random stuff. Any questions on this? Okay, we'll be working with this, so I think things will become more clear. And then what do we want to analyze? Well, we have been most concerned with the square difference between our prediction and the true test targets. And the way we're going to start out our analysis is we are going to condition on the test feature vector x, which means we want to know what happens for a particular test feature vector x as a first step. Once we derive that stuff, then we can say, well, what happens on average? Then we can sort of average over the x's. But first, we want to say for a fixed x, what happens? So because x is random, if we want to fix it, we have to condition on it. So that's how we're going to handle that. And this is the statistical mean squared error, which is similar in spirit to the sample mean squared error, but this guy involves an expectation, whereas the sample one, remember, that had an average over a set of variables. In that case, these could be test samples or something. There was some sort of averaging. But here, because it's statistical, we have an expectation. Okay, so intuitively, what are we trying to do? We're trying to remove the variability that is due to the fact that there's going to be uncertainty on the training parameters. Like, I can design these beta hats if you give me a particular data set. But again, I'm thinking about the data set as random. So I don't have any particular data set. I want to know more what happens like over many, many data sets, many, many experiments. The other thing that we're doing is we're averaging over the test noise, this noise. We're saying, I don't know what that's going to be, so I want to average over all those possibilities. What we're not averaging over for right now are those test features. Those we're just fixing. Okay, so that's what we're trying to do, is derive an expression for this. That's what we'll do on the next page. Are there any questions before we launch into that? Okay. So this page looks kind of intense, but I'll convince you that it's really not that bad. And actually, we'll get to practice all those expectation those two key rules over and over again. So just to start out, we are starting out with the same definition that we have here. So that's how it starts. Next thing, what we're doing is we are just plugging in this model, y equals fx plus epsilon, plugging that in for y. Y equals fx plus epsilon, and we're plugging in for y hat, this f hat x beta hat. Okay, so just applying our definitions. All right, so now let's proceed. So the first step is to group this into two terms. Think about epsilon as one term. Think about this difference of f's as the second term. And let's expand the quadratic. So this is all happening on the inside of the conditional expectation. Okay, so on the inside, we're going to get epsilon squared, right? That's this. We're going to have a cross term, epsilon times this difference of f's. Actually, we're going to have two times that because there's two cross terms. And then finally, we're going to have this thing squared. Okay, so just simple algebra so far. Now, is everybody with me so far? Okay, we can use our first expectation property, which is linearity. We have the expectation of this plus that plus that. So by linearity, we can write this as the expectation of the first plus the expectation of the second plus the expectation of the third. Okay, so here's the expectation of the first. Notice that we're still keeping around this conditioning on x because it might be important. Turns out for this particular thing, it's not important, but we'll talk about that in a moment. Okay, second term, expectation of, the cross terms. Yeah, expectation of this cross term. So the first thing is, remember, 2, deterministic number, we can pull that out. So that comes out. Next thing is what remains, we can use the independence property. We have a product of two different things involving random variables, but we said epsilon, that test noise, is statistically independent from all these other random variables. So basically that means we can split this into an expectation involving epsilon times an expectation involving the rest of the stuff. The nice thing about that is, let's think about what is the average value of epsilon given x. So the first thing is, well, x and epsilon are independent. And what we said is, if they're independent, then conditioning on this does not affect epsilon. So we can, in fact, write this as expected value of epsilon alone. And second, we can come back and realize, oh, that was actually 0. That is a zero mean quantity, so that goes away. Because that goes away, this whole term goes away. Okay, so everybody good on that? So we used linearity and independence property. Cool. So, and then the last term, we're not really doing anything with it yet. We're just taking expectation of that squared term given x. Okay. Next thing to work on is this. So again, epsilon is independent of x. That means that we can write this as expectation of epsilon squared. And this expectation, well, you can use this idea here. Expectation of epsilon squared is the variance of epsilon squared minus the, or plus the squared mean of epsilon squared. So this mean is 0. That means that the expectation of epsilon squared is just the variance, and the variance was sigma squared. So as a result, this thing boils down to sigma squared. Okay. And we said that this term cancels. All right, so next we're going to work on this, but is everybody with me so far? Or any questions? Okay, so let's work on this term. So this is a bit not intuitive, but I'm going to do a little tricky business here. I'm going to subtract a specially selected quantity and then add it again. Obviously, I'm not changing anything. It's like adding 0. So, but the reason I'm doing this is so that I can, again, think of this as a quadratic with two terms and then expand that quadratic. So we are going to get the first term squared. That's this. We are going to get that last term squared, which is this. And we are going to get the cross term of those, which is that last expression. So I haven't really done anything to simplify this, but I did do a simplification of the cross term. In particular, to start out, I would have the expectation of the product of those things times a 2. Well, I could pull out the 2. And now the expectation of the product, let's use this conditional probability idea that since I'm conditioning on x, for the purpose of this expectation, I can think about x as non-random, as deterministic. So that means that this is deterministic. That means that this is also deterministic. So this thing, because x is random, usually this whole thing is dependent on that random x. Even though beta hat is random, when I took this expectation, that sort of removed all the randomness due to beta hat. Okay, but these are a function of x because x is, I'm conditioning on it for the purpose of this expectation. I can think about it as deterministic, and I can actually pull it right out of that expectation. So that's how that came out. And what remains is the expectation of this part, which is down here. So let's take a look at this. Okay, so this part again is actually deterministic because that's a function of x, but I'm conditioning on x. So I could pull that out of the expectation. I would then get expectation of this minus this conditional expectation, but you can actually see those two things are identical. This conditional expectation is this term. So basically when I subtract them, they cancel. This whole thing goes to 0. This whole thing is gone. So we're almost done. The very last thing to do, the last step, is to realize that because I'm conditioning on x, this, I can think of that as deterministic for the purpose of this expectation. Same with this term. And so I actually don't need that expected value here. I just get this part here. So that is what is over here. Okay, this other term, all I've done is I've swapped inside the square. I can swap. I can add a minus sign. So all I've done is swap the order there to make it a little bit more familiar looking. But that is the derivation of this super, super important equation. Let me pause and ask, are there any questions on the derivation itself? Okay, so all we used for this derivation was simple algebra and those two expectation tricks and the definition of conditional expectation. So once you get practiced on that, this should be super easy for you. Now we can sit back and interpret what have we shown. So here is a term that is the irreducible error. Okay, so notice that all these terms are positive, or, non-negative. So basically, it's not like I can somehow cancel this with this other stuff. No, in the best case, I could maybe set both of these to 0, but even if I did, I would always have this. That is why it's called the irreducible error. There's no way to get rid of it. It's just that the mean squared error, because of that noise that is in the test y, there's just no way to ever have a mean squared error less than the variance of that noise. Okay, now the things that we can hopefully minimize through careful design are these two other terms. The first one is called the bias term, or it's actually the squared bias. I'll describe what that means in a moment. And the second is the variance term. Okay, so in terms of the variance, maybe the way to see that is remember that this f hat, a simpler way to describe this f hat is simply, we call it y hat. So if you think about this as expected value of y hat minus expected y hat given x, that's this thing called the conditional variance. So it's just like the variance, but I'm conditioning wherever I take an expectation. Okay, so we'll get into the interpretation of this in a moment, but that's how we got that. And then bias, the easiest way to see this, again, this part here, this was the noiseless y. So because the noise is 0 mean, this is the average value of y given x. So that is where this part comes from. And then this other part just comes from the fact that the shorthand for this is y hat. So that's where this part comes from. Okay, so these last expressions are the most interpretable. So it says, at the end of the day, mean squared error is this irreducible error plus the squared bias plus this variance. So let's interpret this. So this is the difference between the true and predicted targets given x on average. In this case, on average means, imagine you do many, many, many experiments. In every experiment, you had a different training data set, which gave you different beta hat parameters. You had different test noise. And when you average over all those different things, you finally get a number for the average difference between y and y hat. So this thing, as it turns out, is pretty easy in a lot of cases to get this to be 0. Now that if y and y hat agree on average, that does not mean that they agree for every experiment you run. In fact, each experiment you run, in most cases, these will never agree. So unbiased means you're correct on average, but it does not mean you're correct at every instance. Okay, the next thing, what's interesting about this is there is no ground truth label anywhere here. Here we're comparing to the ground truth, the true y. Here there's no true y. All this is saying is how much does your y hat vary around itself on average? That's what variance is. How much does it vary around its center? So the more your y hat varies around its average, the larger your variance gets. Whereas this term measures how close that y hat is to the truth on average. So those are the different ideas. Let me show you just a sneak peek of maybe an intuitive way to see this. So if you're throwing darts at a board and you have this situation, this is a case where you have bias. So this is, your average. This is where you want to be. And you can see that there's a big difference between your average and where you want to be. Over here, your average is agreeing with the target average. That's great, but of course, you're never hitting the bullseye perfectly. You're always somewhere different from it. So on average, you're perfect, but or very close to perfect. But on an instance-wise, you're still making errors. In this case, on average, you're just as good as this. You're still on average at the center, but now per instance, you're making bigger mistakes. You're farther off target. So the difference between these, both of these might have zero bias. This has low variance. This has high variance. Okay. This also has low variance, but the problem here is bias, not variance. Okay, so that's kind of what we have for these pictures. So we're out of time today, but what we're going to do next is we're going to come back to our polynomial demo. And this is a really cool plot, set of plots that I think will hopefully make everything clear in the end. So we'll save this for Friday. And see you guys on Friday.